So in some of the previous videos, we were talking about the comparison between translational motion and rotational motion. And we'd like to carry that further in this video. So when we were talking about the work energy theorem, we introduced the idea of the kinetic energy. And we remember that the kinetic energy was defined to be K is equal to 1/2 mv squared. So this is the term that we would use to describe some mass that's moving along with some velocity like this. Okay, so the kinetic energy for this mass moving with some velocity v is going to be 1/2 mv squared. But this actually isn't the whole picture, because really this is just a block that's moving horizontally. It's translating, as you might say. So this is what's called the translational kinetic energy. So we could put an additional subscript here to denote that this is the translational kinetic energy. So this leads us to believe that there might be another form of kinetic energy, and that's what's called the rotational kinetic energy. So imagine we had some circular object like this that is allowed to rotate. And this is going to rotate about its center with some angular velocity omega, and it has some moment inertia given by I. What we would say for this object is that it has some rotational kinetic energy, such that K sub r is equal to 1/2 I omega squared. Now, if we look at these two terms for the kinetic energy, we can see some parallels between them. And these parallels are consistent with some of the things that we had seen before. Namely, that for translation, we have some mass that's telling us how difficult it is to move something horizontally. With rotation, we have some moment inertia that tells us how difficult it is to rotate something. With the translational case, we have a linear velocity, so the velocity that we learned about when we were doing kinematics, just one-dimensional kinematics. In the rotational case, we have the angular velocity, and that's the rate of change of the angle that we became familiar with when we talked about rotational motion. Okay? So now that we've introduced these two types of kinetic energy, Professor Shepard's going to do some example problems, or an example problem, showing how you can use both of these in an example.
All right, we are going to do an example of a rotational kinetic energy problem. So I've got an object that can roll versus this may have looked like a previous question where we had boxes that were sliding up and down an incline. So now we'll look at this as an object that can roll down the hill versus slide. So let's say we have a solid sphere, something like a bowling ball. It's very, very solid through the inside. It starts, we'll say, at rest at the top of a incline of some height that's known, and we want to predict what speed it's going to have at the bottom of the incline. So one thing, anytime you're mentioned a specific shape of an object that's going to move, having its moment of inertia down ahead of time is a good idea. So for a solid sphere, and this is something that you can just get from one of those tables or the formula sheet, is 2/5 mr squared. Okay, so we'll say that our sphere has a mass of m and a radius of r. All right, and I want to look at this using ideas of energy conservation. So if I think about comparing the top of the hill to the bottom of the hill, if we start at rest and we're above ground, then I'm probably going to say that we're starting off with gravitational potential energy. So that's kind of our initial case. Then, once this thing moves down to the bottom of the hill, this is where we have to look at this slightly differently from where if you had a box just sliding down the hill. Yes, it's displacing linearly, so there's going to be some of that we'll call translational kinetic energy. That was the old kinetic energy that we had. But it's also actively rolling at that point. So we are going to have rotational kinetic energy as well. So going from initial to final mechanical energy, since there's no other external forces on our system, we can say that that's conserved. So I'll say that it's translational kinetic energy plus rotational. So it's the same energy conservation types of things we did before, just adding in this new little piece here. All right, and now I can start plugging some stuff in. So I know that this is mgh, this one is 1/2 mv squared. That's ultimately the v that we're looking for. And then Kr, we just learned, is 1/2 I omega squared. So if I look at the information that I'm given, I probably have the height of this. We're looking for V, mass of the sphere, radius of the sphere, I know how big it is, but I'm missing some of these other things. So this is where those formulas can come in handy. I know that I is really going to depend on the size of the object. So I can get those into the equation and simplify some of my variables. So if I do some substituting, for I, instead of having I'm going to substitute the information in for my shape. And that would be omega squared, okay? And again, I'm not looking for omega, but we need the linear speed here, the translational speed. So that's where, if we remember the connection between linear things and angular things, I know if I multiply omega by r, or angular speed, by radius, then I get the translational speed, or linear speed. So I can substitute that in here. Instead of having omega squared, we can say v over r squared, right? And then I'll carry the rest of this stuff down. Okay. And now I can see a couple things. I've got mass everywhere, so it actually turns out that even if we do know the mass of the object, we don't need it. It's gonna cancel out of the equation. And then if you have v over r squared, then you really have r squared at the bottom here. So your r squareds will cancel as well. So that if this was r squared, that's going to cancel out. And if this was v squared, if we kind of move that on the inside, we can cancel those things. So if I look at what I'm left with, GH equals 1/2 v squared plus 1/2 times 2/5. That's going to give me 2 over 10. So 1 times 2, 2 times 5, and then all this stuff canceled. So I just have v squared. So it's much, much simpler to solve at this point, because we know our height, this is our one known value. Now I have v, which is what I'm looking for. So these can be combined. 1/2 is like 5 over 10. So this can be turned into 7/10 v squared, 5 over 10 plus 2 over 10. Then you can do some algebraic rearrangement. So multiply by 10, divide by 7, and that would leave you with v squared. And then finally you can do the last step, taking the square root, and that would give you v. Okay? So once you know height, you know g, you can plug it in. Now you know what the linear speed is at the bottom. If you needed to know what omega was, then you'd have to know radius to go from there. So we can see that what started off is normal conservation of energy things. After we do some substitutions of smaller equations, we end up getting something that's much more simple. And there you have it for using rotational kinetic energy. See you in the next video.